I'm Yongjoo Baek from Seoul National University. Okay, I've been a bit wondering why I was assigned to this session because I don't do machine learning. Okay, I thought about the connections. So like my talk today is gonna be about like how to make use of some kind of non-equilibrium fluctuations in the environment. So in that sense, this is connected a bit to the first talk. And as for the second talk, just like the TCM theory gives you some intuition about this high dimensional space of the Chinese medicine and the disease, I will try to give you some intuition about what can happen in an active fluid when you immerse some kind of object in it. Okay, so let me start. So my talk is going to be about a generic mechanism for symmetry-breaking motility in a dilute active fluid. I'm not sure that the title was the same. Okay, but anyway. Okay, let's see. Okay, so in the morning, Igor Arns gave a very nice introduction to active matter, but okay, I will just try to give my own take on this concept. So like one of the most very basic example of active particle often cited by people is this Escherichia coli, the E. coli. So as you can see in this movie, this bacterium moves by like a series of persistent runs and tumbles. So it moves roughly in a straight line for some period of time, and then it switches up, it switches its direction randomly, and then moves on again. So so how does this kind of motion differ from the motion of the usual non-active passive particles, like the summer Brownian particle? So in the case of a Brownian particle, it has some kind of mechanical energy in it, but then it exchanges that energy with the surrounding environment in the form of heat or work. And what happens in that case is that you model that kind of motion using this kind of the Langevin equation, which contains the friction and some conservative forces from the environment and also some kind of summer noise. But here, this friction and summer noise are actually related by the fluxation dissipation relation, because the way you dissipate the summer energy into the environment is actually also kind of related to the way you absorb the summer energy from the environment by time reversal transformation. So there is time reversal symmetry between excitation and dissipation of this particle, and therefore this correlation of the summer noise and this friction are actually related by this kind of relation. So a passive particle, which is not active, always obeys this kind of symmetry property. But in the meantime, the Running-Time particle, like the bacterium here, has some kind of separate ambient or stored energy source, which can be converted to mechanical energy. So that kind of motion usually involves some kind of non-conservative or self-propulsion force, which breaks the time reversal symmetry. And also what is important here is that this propulsion is usually related to the direction of this propulsion related to the body shape of this particle. So for example, this E. coli has this oblong shape and it can always propel in along this axis. And of course, it requires some time to change the orientation. So compared to this summer Brownian motion, where the scale of reorientation is comparable to the scale of summer collisions, for this active particle, of course, the way you turn your direction is bound to be usually much slower than this summer time scale. Okay, so there are many examples of active particles, including this soaring bird that was mentioned by the first speaker. And each particle converts stored ambient energy into stationary motion, and they break time reversal symmetry at the particle level, and then their direction of motion is determined by basically their body orientation. So so how can you distinguish like a fluid consisting of these kind of active particles from a fluid without any active particles? So there's one simple method. You can basically drop an asymmetric object like this wedge shown here into the fluid, and then now you can see what happens. So if there are only passive Brownian particles around, then what happens is the pressure applied on this object is the same everywhere around the object. Therefore, this object doesn't show any persistent motion in any direction except for summer fluctuations like the Brownian particle. But when you have these active particles surrounding this object, then these particles tend to move in a straight line for some period of time. It doesn't change its direction for some period of time. And therefore, for the particles which approach this wedge from the left-hand side, then they will be pushed into this concave side, and then you will find it a bit difficult to come out of this, because if you want to come out of this convex area, then you have to really turn your direction by almost a large angle, and that takes time. But in the meantime, the particles coming from the right-hand side just can slide by easily, and therefore you get this density imbalance between the two sides of this wedge-like object, and then this object is propelled to the right-hand direction. And in reaction, the active particles are propelled in the left-hand direction. So this lack of time-reversal symmetry of these active particles, when combined with this asymmetric spatial geometry, then it tends to result in some kind of net force on body and net current of these active particles, which you can take advantage by in terms of some kind of directed motion or useful work. Okay, so here are some like actual video clips showing the phenomena that I just explained, so that you can see this wedge-like object immersed in fluid of B subtilis, and then you can see this thing moving in the direction that I explained. And also, if you prepare this kind of gear-like object in a fluid of E. coli, then it because this chiral asymmetry of this body, that also gives rise to this persistent rotation in some direction. So in all these kinds of situations, what we observe is that these bodies have some kind of built-in spatial asymmetric geometry. Okay, but now the question we wish to ask is whether we always need this kind of asymmetric objects to induce this kind of current or motility. So the short answer is no, and we are going to discuss why. So this is maybe the basic example of where a symmetric object in the initial state can give rise to actually asymmetric motion in the very similar way as I explained before. So here is we prepare some kind of flexible polymer, which of course can be prepared in a very symmetric manner. But then once there is some kind of fluctuation, then that immediately breaks the symmetry. And then in response to the broken symmetry, this thing will move. So that's a very basic example where symmetry breaking can happen and they give rise to a motion in active fluid. There are more complicated examples. So for example, here I'm showing you some system of active gel droplet in a Newtonian fluid. So here there are some like microfilaments like actin, which are like joined together by some like motor proteins like myosin. And then this myosin tends to like grab these filaments and then pull them together. So overall, this kind of system tends to have this polar alignment between these actin filaments, and also these actin filaments always have some kind of contractile stress applied by these molecular motors. So you can basically describe this system using a series of these hydrodynamic equations. But then what you can find using these equations is that when the active contractile stress is strong enough, then, and if you prepare the system in such a manner that they are aligned in they have some kind of polar order, then the strong contractile stress can actually result in some kind of splay instability. So the aligned filaments will develop this kind of asymmetric configuration, and then the asymmetric configuration will give rise to the imbalance of contractile stress, and then that will give rise to this whole droplet moving in some direction. Now, this splay instability can be formed in this manner or this manner, which are just mirror symmetric to each. I mean, they're like related by mirror symmetry transformation to each other, and so this can move in this direction or in that direction, regardless of the polarity. So, so this symmetry breaking motility is an example of like this motility in active matter, which requires some kind of like polar order in the system. Okay. Now these are what we know so far about some active fluid which exhibits some kind of symmetry breaking motility. But now in our study, we are gonna show a very simple toy model which shows that there's actually a much more basic mechanism of symmetry breaking motility in active fluid, which we believe to be possibly very general. So so in our case, this symmetry breaking mechanism doesn't even require any like deformable body of the object, deformable object, or any like pre-existing like polar order of the active matter around the object. And we can simply use a very disordered, like something like either active gas, which these active particles doesn't interact with each other, but only interacts with the object. So we can use even that kind of simple system to observe this behavior of symmetry breaking. And as for the symmetry breaking phenomena, the negative drag applied on this object, tracer object, is the key mechanism inducing the phenomenon. And we observe both continuous and discontinuous transition. So, so here is like a very basic illustration of what's gonna come later. But I'm not gonna explain it now. I'm gonna explain it later. But this is the picture of the basic mechanism. Okay, so basic outline, but maybe I don't have enough time, so I will just skip. So let me first give you the model that we use. So it's a very simplest model. So here we have a one-dimensional system, and I assume for simplicity, I assume the periodic boundary condition. But later I'm going to take this length L going to infinity limit. And then this tumbling rate, the active particles are Brownian tumble particles that I introduced before. So they move either to the clockwise direction or like anti-clockwise direction, and with constant velocity, but they switch between these two directions with tumbling rate alpha over 2. Okay, and as you can notice this triangular object here. So it is not actually what this object really looks like. This actually represents the interaction between the object and the surrounding active particles. So, so when the active particle is on the right-hand side of the object, then it is repelled to the right-hand direction with force constant force F. If it is on the left-hand side, then it's repelled to the left-hand direction with the same force, but opposite direction. So this triangular potential basically represents the potential, interaction potential between active particle and the surrounding, the active particles and the object, as written here in this formula. So using this very simplified model of a symmetric shaped object in an active fluid, we are gonna think about how this object is gonna move in the steady state. Now, the important thing to note here is that we are assuming this object to be actually penetrable by the active particle. So if this object is not really penetrable, so if the active particle cannot move across this object, then the phenomena that we are gonna discuss after this will not happen. So it's crucial to understand that this thing is a bit penetrable by the active particles. Okay, so so we basically model the dynamics using this overdamped dynamics. So the active particle moves according to the interaction force with the object and the self-propulsion, which gives the Brownian tumble dynamics. And we assume that there are many such particles, but these particles don't interact with each other. They only interact with the object. And the object is pushed by these active particles according to the action-reaction force. That's written here. And this object is also assumed to be overdamped. So we just use this mobility coefficient to connect the force and the velocity directly. So the question is, how does this object move in the steady state? Now, so it is difficult to really solve this problem exactly, but still we can have some analytic method. So we are assuming here some kind of mean field approximation. So we basically start by assuming that the object is allowed to move at a constant velocity to some direction. Okay, so then we can assume that the active particles surrounding this object reaches some kind of steady state, non-equilibrium steady state. So to really calculate what this active particles distribution would look like in the steady state, we basically move to the frame of reference of this moving object. And so we are changing the frame of reference, and this frame of reference is this like somewhat like a Galilean transformation, but since this we are looking at an overdamped system with the surrounding medium, doing this change of frame of reference actually results in some kind of fictitious force. So this is not really like the usual Galilean transform. We have this additional force in the direction opposite to the velocity resulting from the change of reference frame. And then with this new force in mind, we can switch this to some kind of master equation-like formulas, and then we can basically solve these equations for the steady state. And for any kinds of potential, we can calculate in principle, we can calculate the active particle distribution exactly under these assumptions, and then calculate the force on the object. But for simplicity, we'll stick to this triangular potential. Now, in the limit of very small velocity at which this object is moved, we can calculate the drag coefficient, and we can calculate it exactly under these assumptions. So that's shown here, this gamma, as a function of the persistent length, which means that the length scale over which these active particles move without changing direction. And this F is like the repulsion force from the object. So they basically indicate the strength of interaction between active particle and this passive object. So here's just some formula, which might not be easy to understand at first look, but here I'm showing this sign of this drag coefficient gamma as a function of LP and F here in the plane. And what you can notice here is that there is a regime where this drag coefficient gamma is negative. So which means the drag force can be parallel to the velocity of the object. So this drag force is strangely pushing the object in the direction of its motion. So that's why we call this negative drag. And this happens when the persistent length is sufficiently large enough, as you can see here. So this, by the way, this is like the renormalized or rescaled persistent length. So one is like when the persistent length is equal to the size of the object itself. So when this persistent length is larger than the object size, then we see this kind of negative drag. And also this repulsion force from the object should be sufficiently small. So then we see this negative drag. So what exactly happening in this regime? So let's try to get a more detailed picture. So let's first suppose we were just looking at like an object immersed in a fluid of passive Brownian particles. Then in that case, the density profile around a static triangular potential would look like this, according to the usual Gibbs distribution. And if we try to move this thing to the right-hand side, then up to the first order correction in this velocity, the density profile will be modified like this, so that there are more particles in front of the object compared to the behind. And this density imbalance will result in some kind of actual pressure drag force. Okay? So the drag force opposes the body motion, which is what we usually expect in a situation like this. But when you have like active particles surrounding the object, then the density profile of active particles actually look like this. It's actually already quite different from what you see in the equilibrium system. So since active particles tend to swim in the same direction for some time, when they meet a wall, then they push against the wall before changing direction. So that results in these active particles developing some surplus density right next to the wall. So they tend to accumulate around the wall as if the wall is sticky to them. But this is all because of the time scale over which they change direction. Okay, now let's add a bit of motion to this triangular potential. Then what happens is that somehow the wall behind the object tends to appear even more sticky, while the wall in front of the object actually now appears less sticky. So the active particles now pile up behind this moving object. So this is basically showing what is happening here. I mean, in response to the motion, these active particles are piling up behind the object to push it even further. So, so here, so we are basically trying to here give a very hand-waving argument about what is happening. So for the object at rest in an active fluid, then what happens is that there are all these active particles swimming around, but then they behave as if they are feeling some kind of effective attraction to the right-hand side and left-hand side and right-hand side of this object. Okay, but now if we add a bit of motion, then from the reference frame of this moving object, then the effective triangular potential actually look like this. So it is a bit steeper here and less steep here. Okay, then that results in the active particles on this right-hand side actually moving more easily to the left-hand side, while those in the left-hand side find it relatively difficult to cross over to the right-hand side. So that combined with these effective attractions, this basically means there is likely to be more active particles on the left-hand side compared to the right-hand side. Okay, so what happens here is that in response to some kind of motion, which can be caused by chance, the active particles are responding to this effectively asymmetric potential in the moving frame, and then they are actually sticking, they're responding in a way which actually enhances this asymmetry. Okay, so so far these were our observations. So these active particles induce negative drag when the Person's length is sufficiently large, and so that mechanism that I just explained, it happens only when this Person's length is sufficiently large compared to the object size. And this is possibly because these one-atomic particles, or these active particles, actually need to sense this effective asymmetry of the potential of this object. So when this active particle changes its direction very often, then it eventually lose what it experienced before by interacting with this object. But so it will be able to really see this asymmetric shape of the object only when it is traveling in the same direction for a long time, sufficiently long distance. So that's why I think we need this large LP here for this mechanism to happen. And also the wall repulsion should be sufficiently small. So if this is not sufficiently small, then very few active particles will really cross over the object, and therefore it will not be able to sense both sides of the object. Then again, we will not see this kind of mechanism. Okay, so I think these are the main two important intuitions about this negative drag happening in active fluid. Okay, so since I just have 5 minutes maybe, so okay, let me speed up. So so I just used the triangular potential to give you an example, but we can check many other different kinds of potentials to see that these things too happens. And to be more really theoretical, we can also assume that the potential itself is very small, and then try to calculate the drag coefficient up to second order potential, and this too gives us some exact result for any potential, and with the very clear result that the negative drag will be induced when the repulsion force itself and the Person's length itself are sufficiently large. Oops, sorry, well, yeah, when this LP is sufficiently large, then we get this negative drag. And okay. So far, I've just shown you that there's really this negative drag thing. But now the remaining question is what would be the eventual velocity of the object in the steady state? So this negative drag is for the case when this object is moved at a very small velocity. But then as they increase the velocity, then there will eventually appear the point where this negative drag will eventually peak and then get reduced and cross over to positive drag. Okay, then there is gonna be some kind of stable fixed point indicating how fast this object would move in the steady state. And this corresponds to some kind of self-conscious equation in the mean field approximation. And then, so okay, I will not really go into this diagram, but okay, here is our most complete phase diagram. So here is the wall repulsion and the Person's length, and as a function of these two, we have many different kinds of possible state behaviors. So this I corresponds to the case where only the immobile state is the stable state. And this blue region corresponds to where this mobile state is the stable state. So this object moves at some kind of velocity. The red regions correspond to mobile-immobile coexistence. So there will be some objects which are at rest. There will be some objects which are moving because those are metastable states. And then there will be even like cases where there are multiple mobile states. So some objects are moving at a smaller velocity, others are moving at a larger velocity in the case. So those regions are like very small regions around here and here. Okay, and what you can expect from this is that there's gonna be some kind of continuous phase transition as we cross from immobile to mobile region around here. And if we cross these red regions, then there's gonna be something like this continuous phase transition. So these are all just kind of mean field approximations, but we can really check that these happen using our numerical simulation. And what you see here is that by making the object mobility coefficient very, very small, then you can actually really go to the regime where this mean field prediction looks very, very good. Okay, and then as a function of this interaction strength, you can see both continuous transition and discontinuous transition. As for the continuous transition, we can observe by finite size scaling that this transition belongs to Ising criticality universality class, actually the mean field Ising universality class, because this is somewhat like this Python dimension, like all the active particles are influencing each other through this this passive object that they interact with them. So this is essentially like infinite range Ising model in some sense. Now we also can check that there's really some kind of discontinuous transition here, and basically to check that we measure the Binder cumulant in the steady state, and then we could see that there's this huge negative dip developing as we increase the number of particles here, which is usually indicated as a signal that there are like multiple peaks, coexisting peaks in the distribution of the order parameter. And we can indeed see that that is happening. Okay, so just to summarize, so we found a simple mechanism by which an object with fixed geometry, the disordered active fluid, can become motile by symmetry breaking. And this negative drag, I think, plays a crucial role in the emergence of such phenomena. And it will happen only when the persistent length is long enough or the particle object interaction is weak enough. Okay, so we believe that this negative drag mechanism that we found by our model is actually going to be very important when it comes to understanding the fluctuations of the forces exerted by active particles on a passive object immersed in it. Actually, there are some other group which were studying very similar system, which recently published these results. And secondly, when the system is very close to like this critical regime corresponding to continuous transition, then we might be able to see some kind of like anomalous diffusion of this tracer particle because of the critical fluctuations. And also, if you try to really see what would happen to the system as we like increase LP, which is equivalent to change the particle size, object size, then you see, we can even get to the regime where we see immobile state, mobile state, and then immobile state again. This might be relevant to some kind of like non-monotonic dependence of the effective diffusion coefficient really observed in this active fluid as a function of the tracer size. Now, the remaining issue is that, the time is up. Okay, so this is some kind of experimental system. I think it's possibly related, but I will not, I'll just explain if you're interested. Okay, thank you.
Yeah, thank you very much. So we have time for a few questions.
Can you connect to the experimental result on the camphor boards?
Yeah. So basically, this camphor disk is doing this asymmetric. So it's like a disk which is slowly dissolving into the water surrounding it. So when the camphor is dissolved in water, then it weakens the surface tension. But then when this thing starts to move slightly, then there's an imbalance of the camber conservation on both sides, and that results in symmetry-breaking motility motion. Now, what you actually see here is a series of camber disks moving in this very interesting manner. And what I suspect is that, you can see that these guys are moving as if they are transporting momentum. But of course, momentum conservation is not really a thing here in this system. What might be happening here is that this camber disk has some kind of two different kinds of metastable state, I believe. So by the impact, it is kind of moving the other disk out of this metastable state and letting it move. So so how this kind of like this two different metastable states can coexist is something that we need to understand by theory, I think. And then what the kind of this conscious transition that you observed in our model, I think, is possibly related to what is happening here. So we wish to delve more into it, but that's for later work.
Yeah, looking forward to it.
Yeah.
Further questions, comments? I have a short one.
Yeah.
Or maybe, hopefully short, I don't know. In the first diagram where you showed the negative drag, there was a L to infinity limit, now a bit up,
Yeah.
which that capital L, yes, over there,
yes,
second
yes.
line, was connected to the definition of the triangular potential. And so I was, I think I missed the meaning of this L going to infinity limit.
No, this capital L is the size of this one-dimensional system. So, okay, basically, we're trying to make sure that the boundary, the finite size effect of the system is taken away from the resource.
Very well.
Yeah,
So that I missed. Okay, thank you very much. So, well, then I think we can thank all the three speakers of this session, and we can conclude this one.
Okay.